In this video, we're going to explore the volume of pyramids and cones. Instead of just me telling you the formula and then kind of running with it, we're going to do a little bit of exploration and kind of develop that formula. So below we have a square pyramid. The sides of the base equal 6 and the height is 12. We want to know, how do we find the volume of this pyramid? Well, first of all, we're going to take this pyramid. We're going to essentially treat it as if it were a rectangular prism. We know the base is going to have side of 6 and the height is going to be 12. So if we were to calculate this as a rectangular prism, then we would just multiply the three dimensions together, 6 by 6 by 12, and that would give us 432. Well, the reality is a pyramid is essentially just a bunch of different prisms stacked on top of each other. So let's take a look at this sketch we have here. And in this sketch, what we have is a rectangular prism, and as we add more rectangular prisms to this stack, what we end up getting is something that looks more and more like a pyramid. What happens with these rectangular prisms, as we add more of them to approximate this pyramid, the height of it is going to decrease for each prism. The overall height's not going to change, but the height of each prism is going to change. And the dimensions of the prism for the base are going to change as well. So you see where we have this large rectangular prism. Now we have one that's kind of been cut in half, and then another one that's even smaller than that. And as we add more and more, at some point, it gets almost indistinguishable from a pyramid, very, very close to it. So we're going to follow this line of thought to approximate the volume of the pyramid, see if we can generalize and make a general formula for this. Well, first thing we did is we took that pyramid, broke it into two rectangular prisms. And to do this, we're actually applying a calculus principle here. You not really need to know what this is at this point, but it's called a Riemann sum. And essentially, we're going to take a larger shape and then use smaller and smaller approximations to get pretty close to the actual volume of the shape. So, again, we got to remember that number 432 because we're using that a lot. Find the volume of the two prisms added together. So we have a one prism here. Prism A in the bottom has dimensions 6 by 6 by 6. So we've cut the height in half, but we haven't changed the dimensions of the base. But in prism B, we have cut the dimensions of the base in half and also the height in half. So we find the volume of each of those and add them up. We end up getting 270. We want to know, all right, what's the ratio between this approximation and that rectangular prism that we start with, which we know is going to be a bad approximation because it doesn't look anything like a pyramid. 0.625, so about 63%. Well, we're going to add more. We're going to do 4 prisms. Same idea. Now we've cut that height in half even further, and those dimensions of the base are going to be cut in half even further. So when we end up finding the volume of this, we get 202.5, just finding the volume of each of these 4 rectangular prisms. When we add those up, we get the 202.5, which is about 46.9% of the original rectangular prism. So you can see that number's going down. We're getting smaller and smaller. Do it more with 8 now. And I'll save you the gory details of it. But essentially, we're going to calculate the volume of these 8 prisms, add them up. We get 172.125, which we can tell is smaller than what we just had for this volume, but not significantly smaller. So now we're looking at about close to 40% of the original. 16, I'm not going to show you the dimensions here on this because it would take about a page to do. But essentially what we're going to do is do the same idea, but now we have 16 prisms instead of 8. So just twice as many prisms. And we end up getting 157.78125, which is about 0.3652 for the ratio, about 36.5%. Even worse, if we go to 32, we have twice as many than the 16. So we end up with 150.82. Again, you notice they're not really changing by much here. 157 compared to 150, not a huge difference. But essentially, we're down to 0.3491. What we want to know then is, using those numbers that we have, it looks like they're approximating to 1/3. If we added more and more and more and more prisms, eventually we get pretty close to 1/3 to be indistinguishable. So what that's telling us then is that the volume of the prism is 1/3 of the, the volume of the pyramid is 1/3 the volume of the prism that we used as our original approximation. So the way we calculated the volume of a prism was we took the area of the base and we multiplied by the height. So our volume formula then for a prism, any prism, whether it's a square, rectangle, triangle, hexagon, any of those, it's going to be 1/3 the area of the base times the height. So again, 1/3 the area of the base times the height. It turns out it works the same for cylinders as well. I'm going to show you this sketch with a cylinder so you believe me. But essentially we have one cylinder here that we're going to use to approximate cones. So we start with a one cylinder because, again, it's just like a prism but with a circular base. If we start adding cylinders, again, we're going to cut those in half for the heights and everything. And we end up getting, something that is going to start to look more and more. Right now it looks kind of like a wedding cake, but as we add more and more pieces to it, we end up getting something resembling a cone. Again, as we add more and more, it's almost indistinguishable. It gets very, very close to that cone shape. So we're going to follow that same process, but here we're telling you that essentially, yeah, you know what, the volume of a cone is the same idea. It's 1/3 the area of the base, and the area of the base is a circle, so it's pi r squared, times the height. So the way we're going to start this one is we're going to give you the dimensions. The radius is 3, the height is 5. We're going to ask you to calculate the volume. So we get us 15 pi, but for our purposes, the decimal in this case is going to be better for us because we're going to do some things with it to calculate what's called error. And it's 47.1239. To find error, you're going to take the actual volume that you calculate and subtract off the approximated volume. Then take the absolute value of that, because we just want to know how far away from the original is it actually going to be. So with one cylinder, the actual volume was 47.1239. The cylinder, with a one cylinder as an approximation, is 141.3717. A terrible, terrible approximation. 94.248 we're off by. Essentially twice the volume is our error. That's bad, really bad. So we're going to add in some more cylinders. We went with 5 this time because it works out a little bit nicer for this particular cone. And we found out the volume using 5 cylinders would be 62.2035. Subtract off the 2, and then our error jumps down from 94 with 1 cylinder to 15.080 with 5 cylinders. So as we're adding more cylinders, we expect that our error is going to decrease and it's going to get smaller and smaller until eventually it becomes pretty close to 0. And that happens pretty consistently. So we go to 10 cylinders now, we're at 54.4281. Our error, pretty much half of what we had, 15 down to 7.3 for our error, just subtracting the 2 off. Again, as we add more and more, if we want the error to get smaller and smaller, our process is going to be, we're going to use more cylinders to approximate. And believe it or not, that's a calculus concept, that if we want smaller error, we have to have so many approximations to guarantee that error is less than a certain number. So let's put this into practice. Now that we know that the volume is 1/3 the area of the base times the height, let's take a look at a problem like number 2, where we give you the dimensions of the base and the height, and we actually want you to calculate the volume of it. So the way to do this is you're going to calculate the area of the base first. In this case, it's 6 squared, 36. And then the volume of that is 1/3 the area of the base times the height, which in this case is 8. Now, here's the thing. It really doesn't matter if you find 1/3 of the area of the base or 1/3 of the height or 1/3 of the product. Do whichever one is easier, but only do it to one piece. In this case, 1/3 of 36 is pretty easy to calculate. It'd be 12, and then 12 times 8 would just give me 96. So I figured that one was a pretty